welcome to the lecture on RANS equations. So, RANS is Reynolds averaged Navier-Stokes equations. So, this equation we are going to particularly discuss because when we deal with the turbulent flow. So, as we know that in the case of turbulent flow you have the mean component and also at the same time you have the fluctuating component. Now, the presence of these fluctuating components they give rise to extra set of terms when we deal with or when we talk about the momentum conservation equations or momentum equations. So, in this lecture we are going to see that how when we talk about the turbulent flow. So, what are those additional terms which are coming, and then that is why so we are averaging, there are averaging principles, averaging rules are there, because of that certain extra terms are coming. So, how then these Navier-Stokes equations change, so that we will see here, and that is why they are known as the Reynolds averaged Navier-Stokes equations. So, if you if you talk about the fluctuating parts of the velocity. So, what happens that because of that you will have the fluid layers which will be experienced the additional turbulent shear stress, that is known as the Reynolds stress. So, you can understand it like what happens that when you have these fluctuating parts, or you have if you take the turbulent shear type of flow. So, in those cases if you try to see the the velocity gradient in case of turbulent shear flow. So, you will have the velocity gradient like this. So, you have the velocity gradient in the y direction. So, there is a gradient in the velocity, and if you talk about, if you consider the control volume. So, what happens due to these fluctuations? So, what happens, you will have the formation of eddies, and these eddies on the boundaries they will be looking like this. So, they will be moving like this. So, you will have increase in the y velocity in this direction and decrease in the y velocity on this side. So, so this way due to these eddies. So, in this side you have the fluctuating component will be more than 0, and in this side your fluctuating component will be less than 0. So, this is the velocity fluctuation due to the eddy formation, and you will have the turbulent eddies at many places which will be going on. So, so what happens, or if you talk about this surface, suppose, so you will have again the eddies moving in this fashion. So, you will have on this side V prime is less than 0, and this will be V prime more than 0. So, actually what is happening now in this case, what you see. So, these are the these are the turbulent eddies, and these eddies are responsible for creating very strong mixing inside. So, and they are responsible also for the momentum exchange due to the convective transport. So, these are done by these eddies, and which will be causing the faster fluid layers to be decelerated and slower moving layers to be accelerated. So, the faster moving layer which is their top. So, it will be there will be a braking effect on that. So, that will be subjected to some deceleration, and the slower moving layers will be there which will be subjected to some acceleration. So, so that happens to the velocity component, and even that is happening in the presence of these temperature or concentration gradients also. So, these eddy motions will generate the turbulent heat or species concentration fluxes. So, basically as you see that we have seen that this is along the turbulent this control volume boundaries, there will be you can see the eddies how they are going out, or inside. So, they will be across that control volume boundaries, they will be transport. Now, these things basically these so what happens that they will have the there will be generation of additional shear component, and you will have the additional shear stresses will be generated, and this would due to this turbulent, and that is why they are the turbulent shear stresses, and these shear stresses are known as the Reynolds stresses. And and there are many more we will see that how these fluctuating components. So, these presence of these Reynolds stresses, they need to be accounted when we deal with the conservation equations, especially the momentum equation or even the continuity equation. So, we need to see that, and these extra terms will be coming into the Navier-Stokes equations, and they will be calling as the Reynolds averaged Navier-Stokes equation, because what happens that the velocity will have two component, one will be mean component, another will be the fluctuating component. So, ultimately when you are going to have the momentum equations, so you will have certain components coming into additionally because of these fluctuating parts. So, we will be talking about these Reynolds averaged Navier-Stokes equations. Now, before that we must we know that if you talk about the fluctuation components, so you will have so it's average. If you talk about the fluctuating part only, so it is we have to consider the certain points, that if you talk about the fluctuating part, and if you take the average of this, so your average of the fluctuating properties, so that will be so for the fluctuating part it has to be taken as 0. So, if you take another property like psi, so for that also if you take the average of the fluctuating component, it has to be it is taken as 0. So, as we know that you had the components, so you have the mean and then you have the fluctuations. So, if you take the average of this on the time scale, so it will be taken as 0, because you have the fluctuations above as well as the below. So, you will have this part we will be taking summation derivative that we are taking as 0. If you talk about the other things, like if you have the del psi upon del s, and if you take the average, so that will be nothing but del of phi by del s. So, so that way we take it as these values. So, that will be mean part, and then you have similarly if you have the part like this plus this. So, its mean will be so you are taking the its mean plus the mean separated. So, there are certain properties which we will be using it while we discuss about it, and similarly you will have so basically you need to know certain when we do the time averaging. So, at that time that we will need to use, like if you have the two properties and if you are taking the average of this product, so it will be phi psi plus phi psi phi prime psi prime. So, its average. So, because it is not going to be equal to 0, you can have other component also where one of the properties mean will be taken, fluctuating parts mean will be taken. So, that will be anyway automatically 0. So, these are the concepts which are to be used for that. Now, if you go to the other properties, like so that is known as the cumulative commutative property. Now, For any fluctuating vector quantity A, which is taken as its mean part and also its fluctuating part A prime. So, similarly you take as you have one scalar, fluctuating scalar, and this will be taken as the mean part plus the fluctuating part of this scalar quantity. So, what happens that if you take the dive of A, so its mean will be dive of A. So, this will be its mean part and this is the fluctuating part. So, if you take the dive, so this part will be anyway 0, because as we have seen that its change with time will be or with any if you do averaging it will be 0. Similarly, if you take dive of psi A, so it will be dive of phi A, so that is its mean parts product, and then it will be dive of psi prime A prime and its mean. So that way these also need to be kept in mind to us. So, similarly dive of grad psi, so and its whole mean, its averaging, that will be giving us dive of grad mean part. So, basically this is the mean part. So, we are having the mean part. So, that is so because when we use these equations, when we are going to take the any quantity as the summation of the mean quantity and the fluctuating part. So, at that time these expressions will be required. Now, if you try to see the the Navier-Stokes equation. So, if you try to find the instantaneous Navier-Stokes instantaneous continuity as well as the Navier-Stokes equation for vector u. So, in that case your equation becomes dive of this is u, that will be 0. Similarly, you will have this is your instantaneous continuity equation. Similarly, you will have Navier-Stokes equation that we have already seen. It will be dou u by dou t plus dive of uu, and this is basically bold one. So, bold one means this will be sum of the two quantities, one is mean quantity as well as one is the fluctuating part. So, dive of uu, that will be minus of 1 by rho dou p by dou x plus nu of dive grad u. So, that way what we see. So, this is your x momentum equation, that is what you get this x component equation. Similarly, you have the y component and z component. So, you will have dou v by dou t plus dive of v and u. So, this will be again the bold one, and that will be minus 1 by rho dou p by dou y plus nu and then dive and grad of u v. So, that time it will be v. So, then similarly, if you take the w momentum equation. So, that will be w by dou t plus dive of w u. So, this is again bold one. So, that will be minus of 1 by rho dou p by dou z plus nu of dive of grad w. So, that way we use these are the instantaneous this is the instantaneous continuous equation, and this is the Navier-Stokes equation. These are the Navier-Stokes equations in the Cartesian coordinate system. So, that the velocity vector u, that is this is the u, it has 3 components u, v and w. So, this u has 3 components that u, v and w, and in that case your this will be your instantaneous those equations. Now, when we talk about the turbulent flow, So, in that you will have the mean component as well as the fluctuating component. So, when we talk about these variables, so what will happen? You will have the Reynolds decomposition. So, in that what is done is this u, as you see. So, you will have the component u, v and w, and also it will have the fluctuating component. So, u will be the mean component plus this is the fluctuating component. Similarly, its x component is u. So, that will be mean u plus fluctuating u, that is u prime. V will be mean v plus fluctuating v, that is v prime. So, that way you have to take these components taken together. Now, we have to use the time averaging and then we have to apply those rules. So, if you go for the continuity equation for the mean flow. So, continuity equation if you find, and especially for the incompressible flow. So, in those case what is happening, your dive of this u prime will be basically 0. So, ultimately your equation of continuity for the mean flow becomes dive of u equal to 0. So, dive u equal to 0, that means that dive of u equal to 0. So, this is giving you the continuity equation for the mean flow. Now, we have to find the equation for the x momentum, y momentum and the z momentum, and we have to do the time averaging of the individual terms. So, if you do some homework, what we see that if you find the dou u by dou t. So, as you know that u will be capital U plus u prime. So, it will be basically capital U by dou t, because u prime dou u prime by dou t will be 0. So, that will be 1. Similarly, if you find the dive of u and this u, and that is averaging of this. So, it will be dive of capital U and this will be bold one, and then it will be plus dive of u prime and this will be the bold component, that is prime. So, that way whatever we have studied earlier, similarly minus of 1 by rho dou p by dou x and its average, that will be again it will have the minus of dou capital P by dou x. So, that is again mean component will be coming into it. So, if you substitute these values, what you see in that case these time averaged momentum equations, if you substitute into it, your equations will become like dou of u by dou t. So, you see what happens that we have seen these equations here. Now, in this case this u will be dou u by dou t will be so that you should dou u by dou t will be its averaging will be capital dou u by dou t. So, that will be seen here. So, dou u by dou t is coming. Now, the dive of u, that will be dive of u plus dive of u prime and bar. So, that is what you have seen here. So, from this line you can see that in place of the one term you are getting two terms in this case. Rest of the term comes like this, you have minus of 1 by rho dou p by dou x, this p is the mean pressure term coming here, and then you have the term nu of dive of grad u, again u, this term is coming. So, this is the x momentum equation which is coming basically when you are doing this time averaging, and in that you see that you have otherwise if you look at these equations. So, what you see, it has 4 terms. These 4 terms are similar to it has some similarity, these 4 terms. However, you have one extra term. So, that is there in all these cases. Now, what is this? So, this basically term u prime this is basically the extra term which is coming. This is the stress component, that is because of the turbulence, the fluctuating component, and this is the turbulent shear stress which is coming into picture. Now, how if you try to if you try to expand it, so it will be and if you try to have the generalization. So, what we do normally, that we keep these terms on this side and we take these terms on the on the other side. So, what happens, this will be negative terms. So, what we do, we take the plus terms and we take the negative sign. So, what we do normally, because it is the these components. So, as we discussed that this is the additional term which is coming because of the turbulent fluctuation, fluctuation component, and this is because of this stress component. So, what we do now, customarily we try to shift it towards the right hand side, and if you try to put them towards the right hand side, so you will have dou u by dou t plus div of u, it will be equal to minus of 1 by rho dou p by dou x plus nu div grad u and minus of div of u prime. Now, if you find u prime will be, so you will have the u prime, v prime and w prime component here, and then you are getting the div part of it. So, you will have u prime square plus u prime v prime plus u prime w prime, and then we are getting the div of it. So, dou by dou x plus dou by dou y plus dou by dou z will be coming. So, if you try to write, if you take these turbulent stresses on the right hand side, then your equation becomes like dou u by dou t. So, that will be the first term. Second term is as usual. So, you have div of u and this will be the bold u. So, that will be so you will have this is the bold part. So, then that will be the again 1 by rho dou of capital P by dou x, again mean pressure has come here. Then you have nu of div of grad u. So, that is coming further, and then we have the another term that is 1 by rho of now this is your component which will be, you are taking the div of those components. So, that will be dou of minus of rho u prime square by dou x. Similarly, dou of minus of rho u prime v prime by dou y plus dou of minus of rho u prime w prime by dou z. So, this basically these terminologies will come if you try to expand it. So, because this u prime will be u prime plus v prime plus w prime, this bold u. So, that will be u prime plus v prime plus w prime. So, it will have u prime, so u prime square, and then u prime v prime plus u prime w prime, all the averaging will be done, and its div. So, we will have dou by dou x plus dou by dou y plus dou by dou z. So, that will be coming. So, that is what you are getting, these three terminologies which is coming on the right hand side, and this is basically the this is because of these turbulent shear stresses. So, if you have the further, if you try to write these equations, so you will have for the v momentum, you will have dou v by dou t plus div of v u. So, you will have v u. So, this is u is bold, and that will be minus of 1 by rho dou p by dou y, and then you have nu div of grad v. So, and then you will have again 1 by rho, and now this time you will have dou of minus rho u prime v prime by dou x plus dou of minus rho v prime square. So, that will be again here, and by dou y plus dou of minus rho v prime w prime by dou z. So, that will be coming. So, this way you will have three equations. These these extra stresses, these terminologies which we have taken from the left hand side towards the right hand side, your equation becomes like this. So, you will have dou w by dou t plus div of w u. So, that will be minus of 1 by rho dou p by dou z plus nu of div of grad w, and then you will have plus 1 by rho, and then this time you will have dou of minus rho u prime w prime. So, that will be coming now by dou x plus dou of minus rho v prime w prime, and its average part also, and that will be divided by dou y plus dou of minus rho w prime square, and that will be divided by dou z. So, that is this way you are getting these same equations, but then these once you expand it and take towards the right hand side, because all the stresses we are taking on the right hand side. So, that will give you these three equations. Now, if you look at the equations, this minus of rho, this is u prime, this is basically u prime square. Now, this minus of rho u prime square, so this is basically tau xx. Similarly, minus of rho u prime v prime, it will be tau xy. So, so because of that, so that is why we can write tau xx, that we write as minus of rho and u prime square. So, that is your this is the turbulent stresses. For that you have and then you have tau xy, this will be minus of rho u prime v prime. Similarly, you have tau xy is tau yx, and similarly tau yy will be minus of rho v prime square, averaging of that, and tau zz will be actually minus of rho w prime square. So, that way, and you have tau xy similarly, so that will be same as tau yx. Similarly, tau yz will be minus of rho v prime w prime, actually v prime w prime. So, that will be tau zy, and similarly tau xz will be minus of rho u prime w prime, and that will be tau zx. So, this way these stresses term are appearing on the right hand side, and these are known as the Reynolds averaged and Navier-Stokes equations. Now, if you try to find the for any extra turbulent term which will be because of the transportation of certain scalar quantity like temperature or so. So, in those cases you will have the time average transport equation. So, for that any scalar quantity, transport scalar quantity psi. So, for any this of the transport scalar quantity psi, you will have these time averaging equations. So, you will have the mean part of it will be dou phi by dou t, that will be mean part f phi plus psi prime. So, that we have discussed, that will be this plus div of phi, and you will have the u, that is bold one, so a convective term, then that will be again minus 1 by rho and div of tau phi. So, this is and this is grad of the mean part, and plus you will have minus of dou of u prime phi prime. So, by dou x, similarly v prime phi prime by dou y, then w prime phi prime by dou z. So, this way you will have the transport equation for any scalar. Normally we will have the equation for the temperature or any other quantity when we have. So, we normally have these equations also. This is so this is what you get normally. This is the extra term which you are getting. So, these are the equations. These are known as the Reynolds average Navier-Stokes equations, because we are doing the averaging and we are taking that fluctuating part into component, and this will be used while we try to study or try to model the turbulent equations or turbulent flows. So, that we will see in our coming lectures. Thank you very much.